The next session for today is updatable NIZK from non-interactive ZOPs. Okay, ZAPs. So this session or this presentation is going to be streamed, or not going to be streamed, it's going to be televised. So we have a video for it. And if you have any question later on, okay, you may raise your hands, no problem. We will try to do our best to answer the questions. So, is the system ready? We will start? Good. Okay, let's go. Thank you.
Hello, everybody. As you can see, the title of our paper is Updatable News from Non-Interactive ZAPs. This is joint work with Navid Bayedi, and the current version of our paper is available on this IACR address. So this is usually happens in our daily life for each of us, that we need to prove some statements. For example, we need to prove that we have a valid driving license from an authority. Or sometimes we need to prove that we are plus 18 to get access to some services. Even here, I mean, there are some, I mean, you have some UAE pass systems that basically allows you to prove, I mean, identity of yourself, I mean, to get access to some services that the government or different companies are providing. Or in recent, I mean, new applications like as blockchains, so we have privacy preserving cryptocurrencies or smart contract systems that we have privacy preserving ledgers. Sort of we need to prove that we do the transactions or, I mean, any communications correctly, but without revealing so much secret information about ourselves, for example. Or in different applications, we need to prove that we did some, let's say, payments correctly, and without, again, revealing so much information about ourselves. Almost in many applications, we need to prove that we know some secret key, or we have done some secret computations without revealing the necessary, I mean, let's say, additional information about our secret key. So in this paper, we will use ZAPs. So let's have a short overview on them. A ZAP is a public coin, basically two-party and also two-round protocol, which starts with a verifier and then continues with the prover. And this A and B together consist, I mean, build the proof. And finally, the verifier verifies that if this proof is a valid and returns accept or invalid. So the cool thing about this primitive is that they don't require a trusted third party. And that's a nice thing. But similar to other proof systems, they need to be complete. Basically, honest prover should convince the verifier. And they also need to achieve some security notion against the malicious verifier. And here they achieve witness indistinguishability, which basically guarantees that this honest verifier will not be able to distinguish the witness that is used in proof generation, for example, witness 1 or witness 2. And in the cases that the prover might be malicious, we expect again to achieve some security notion, which is called soundness, and that guarantees that the dishonest prover will not convince the honest verifier. So that sort of primitives, let's say ZAPs, are two rounds, but in practice, sometimes we need to have non-interactive ZAPs, and that sort of basically proof systems are just one, let's say, single message from the prover to the verifier, as you can see here, and it's called proof. And that allows, again, to achieve completeness, witness indistinguishability, and soundness as before. And again, it doesn't need to have a trusted setup, let's say. In practice, it's interesting that sometimes we expect to achieve even stranger notion than soundness, which is called null soundness. Sometimes we expect this in some protocols that they want to achieve stranger security notions. These sort of proof systems are also called proof of knowledge. For that reason, this sort of needs also called non-interactive ZAP of knowledge. And this first time presented by Futzpower and Auro in 2018, that they showed that a variant of basically this Kuratov-Stropsky and Sahai ZAP, non-interactive ZAP, can also satisfy this property. And this primitive non-interactive zaps and non-interactive zaps of knowledge are shown to be very interesting, I mean, very useful in design of various cryptographic protocols. And this paper also is another example and application of them that we will see how. So we mentioned that non-interactive zaps and zaps of knowledge achieve witness indistinguishability. But in real life, sometimes we need something stronger, for example, zero knowledge. And we can achieve this in non-interactive as zero knowledge arguments. This is, again, a proof system which can achieve soundness and completeness, but additionally can achieve zero knowledge, which basically allows to the party to prove the statement, but without revealing any information of the witness. These sorts of proof systems are shown to be, possible to build in two models. Well, the first one is called random oracle, which basically both prover and verifier needs to get access to a random oracle. You can think of it like as a secure hash function, and then execute this random oracle query to this random oracle, let's say, during the proof generation and proof verification. But the second model is called common reference string model, which basically requires to have a common reference string shared between the prover and verifier, and in let's say recent and more efficient constructions, they need to have a structured reference string, basically generated by a trusted and third party and shared with the parties. So in the rest of presentation and this paper, we will focus on this sort of constructions because they are shown to be more efficient. So yeah, as I mentioned in the CRS model with basically more efficient construction, there is a trusted third party who generates gets this language, that relation that you want to prove, and then generates CRS and shares with the prover and the verifier, and also samples some secret information to generate the CRS, which we assume that she destroys them. So as we said, again, similar to the ZAPs, this requires to achieve completeness that we define. But in the cases that the verifier is malicious, we expect to achieve zero knowledge. This is stronger than witness indistinguishability because not only the verifier, let's say malicious verifier, cannot distinguish between two witnesses, but also, the adversary cannot learn anything about the witness. And usually in practice, this is proven by constructing a simulation algorithm that, given the trapdoors of the setup phase, let's say the CRS, it can simulate the proofs and also the setup phase. But in the cases that the prover is malicious, similar to the previous case, we have soundness and sometimes even stronger notions like a knowledge soundness, which I mentioned, that this guarantees that the dishonest prover cannot convince the verifier unless basically he or she knows some secret witness. Even sometimes we expect something stronger than this, which is called simulation soundness or simulation extractivity. Simulation soundness can be considered as an amplified version of soundness, and simulation extractivity can be considered as an amplification of knowledge soundness against an adversary who has seen arbitrary number of simulated proofs. These notions are interesting in the sense that because they can guarantee the non-malleability of proofs, and in some applications, for example, in universally composable protocols, we sometimes expect to achieve this in the underlying disk. And to prove that some protocols achieve knowledge soundness or simulation knowledge soundness or simulation extractivity, we expect to construct an extraction algorithm that can extract a witness from the adversary. So these notions that we just reviewed achieved usually under a trusted setup phase in the CRS model. So, but what happens if really this guy, this lady is not malicious, that's not honest, and she is a malicious, so let's say CRS generator. So this was studied by Belar, Fuspauer, and Scafuro in 2016, and they presented some negative and positive results. So in a good way, I would say that the best result that they presented is that they defined a new notion, which is called subversion zero knowledge. And they showed that we can achieve subversion zero knowledge and soundness at the same time, which basically means that prover doesn't need to trust to the third party who generates the CRS. And the protocol guarantees zero knowledge, even if this CRS is generated by an adversary. But this is still, that this is very nice result, but this is not sufficient to bypass the need for a trusted third party. Basically, the verifier either needs to generate the CRS himself, but if we have more than one verifier, so they need to trust one party who generates the CRS. So one natural approach was just using MPC to reduce this trust. And basically, instead of trusting one party entirely by verifier, the verifier trusts to one of these end participants in the protocol, but still the prover doesn't need to trust. So in 2018, Grat et al. Used a combination of MPC with the subversions range, and they say that, okay, we can construct a new ZK snarks, I mean, in a new model that they called it updatable CRS model, which again, the prover doesn't need to trust to the CRS generators or any, I mean, number of parties, but the verifier still needs to trust one of them. But the possibility, the good case about this protocols was that it's possible for verifier to join this MPC email later. Basically, you get the CRS, you update it, and you don't trust to third party. You just trust yourself. So this was studied in the Grat 18 paper, and they showed that we can achieve subversions range and updatable knowledge soundness. Basically, the prover doesn't need to trust. The verifier only updates the CRS once, and we achieve zero knowledge and knowledge soundness. This was amplified in follow-up results. Basically, they showed that we can achieve updatable simulation extractability even with subversions range. But all of them are focused on snarks that they require some subversion resistance or updatable knowledge sound snarks as an input protocol. I mean, this studies. In this paper, so we start with non-interactive ZAPs. This technique was first time proposed with Baghery, and Scafuro, and we basically show that this idea can be extended to build basically subversions range and updatable sound or updatable simulation extractable or updatable simulation sound NISQ arguments. Some of them are for first time, but some of them already are presented. Let's say updatable simulation extractability with subversions range was achieved, but this is first time that we achieve subversions range and updatable simulation sound and simulation and sound in a NIV. I mean, let's say in a NISQ argument. So let's see how this Baghery, Scafuro built subversions range and sound NISQ. In the standard CRS model, we know that there's a trusted third party who generates the CRS and provides these trapdoors to the simulator. And in the case of proving zero knowledge, we assume that this verifier is malicious and we simulate the proofs and the setup phase. But they started to consider, what if this party is malicious? Then we cannot trust the trapdoors and CRS. So then prover also, I mean, cannot get sure that the proof is zero knowledge. So to deal with this problem, they started to define a CRS as a tuple of knowledge assumption. And then they showed that since a knowledge assumption, we can verify it. So if this tuple verifies, then we know that this adversary should know these trapdoors. That allows basically the simulator to extract the simulation trapdoors directly from the malicious CRS generator rather than getting it directly. I mean, basically, because you don't trust this, you extract them. But what about the CRS? So for that, we need to get sure that it's safe. So they provided a CRS verification algorithm that gets the CRS and checks its well-formedness and the validity and returns either 1 or 0. So the prover uses the CRS if this algorithm returns 1. And if you go inside this algorithm, basically it has some verifications by pairings that, for example, we need to check the well-formedness of the CRS tuple, and also if the CRS is large, so we need to get sure that the other part of the CRS is consistent with these 3 elements. So then they show that if we use a non-interactive ZAP to prove this language, let's say the prover is asked to prove that X belongs to language, or I know the CRS trapdoors, let's say trapdoor S0 or S1, one of them is enough. So, but since this is supposed to be hard to extract this S0 or S1, so basically the honest prover needs to know this, but this also, since we can extract the trapdoors, this allows to simulate the proofs for this language. So they show that this construction achieves subversions range and soundness. And they had some challenges to prove that we know the CRS trapdoors, but they again managed to deal with, that by some another knowledge assumptions in the reduction of sounds. This was for a NISQ. The results of Baghery, Scafuro. The 2 follow-up works, in one of them, we extended this results to the ZK snarks, and we presented a variant of state-of-the-art Grat 16 snark under different knowledge assumptions that could achieve again subversion range and knowledge soundness. This result can be considered as an amplification of previous result in the sense that we improve the efficiency of protocol and we also achieve knowledge soundness rather than soundness. So you see that constructing CRS verification for CRS of snarks can be more challenging than constructing the same algorithm for a tuple of knowledge assumption. In a follow-up work, I showed that given such snarks, we can define an OR language and extend this result to the NISC arguments that can achieve subversions or and stronger notions like as simulation soundness or simulation extractivity. But again, you see that the verifier still needs to trust the CRS generator, or he needs to generate the CRS himself if there is only one verifier. But usually in practice, we have more than one verifiers. So to deal with this problem, in 2018, Grot et al. Introduced a new model called updatable CRS model. And this updatable CRS model, as it comes from the name, allows the parties to update the CRS. And sort of you are injecting your secrets to the CRS generation. You can look at this as a full three-shot secret sharing scheme that as long as one of these shares are not revealed, so the protocol should be secure. And they define a new notion that I mentioned, updatable knowledge soundness, and they show that okay, we can prove that under this CRS update algorithm and CRS verify that allows the parties to update the CRS and verify its well-formness. Again, this protocol achieves subversion range and updatable knowledge soundness. This basically allows the verifiers also bypass the trust on a third party. Already we know that prover doesn't need to trust entirely, and also she doesn't need to update the CRS because any protocol which is secure under entirely subverted CRS should also be secure under an updatable CRS, because in updatable CRS you assume that one party is honest. So a similar OR compiler was presented later, in two follow-up works, and they showed that such NISCs can be improved, let's say lifted to achieve subversion range or updatable range with updatable simulation extractability. In these two works are used using ZK snarks. Still, their CRS is linear, and they require the input NISCs to achieve subversion range. So how we use this idea, this updatability? So recall this protocol from Baghery and Scafuro protocol. So you see that they define the CRS as this tuple of knowledge assumption, and they prove that this protocol can achieve subversion range and soundness. But in this paper, we observed that we can extend this idea and we can define CRS updates that would get this CRS and will update it. And then also we'll give a proof that I did the update correctly. And then the parties will be able to verify this update by some similar CRS verification, but it's a slightly extended version of this one that here, because you have some intermediate updates that you need to verify. Then we prove that this protocol can achieve subversion range and updatable soundness if we start with non-interactive zaps. But if we start with non-interactive zap of knowledge, their compiler, basically their technique, can be also used to build subversion range updatable knowledge soundness. So yeah, as I mentioned, this can be done, for example, with non-interactive zap of knowledge or non-interactive zaps. So if you go inside this our algorithms that we proposed for Baghery-Scafuro protocol, so in the CRS update, we sort of just randomize this CRS. So you see that we sample new S0 prime, S1 prime, and just we randomize this algorithm as a CRS, and we return these elements in group one, the group as a proof. So we show that this allows us to verify the CRS updates, and the details are provided in the paper. But under this two algorithms, using this algorithm under the same assumptions without adding a new assumption, they also use Diffie-Hellman knowledge of exponent assumption. We can prove that this protocol achieves subversion range and updatable soundness or updatable knowledge soundness. And these primitives are the first updatable zero range and updatable soundness argument. By now, we hadn't such protocols. And the cool thing about it is that by now we only had, in the CRS model, we had NISCs that they had CRS of length order of n square, which n is the number of multiplication gates in the circuit. And in the base case, we had CRS of size linear, but in the random oracle plus CRS model. And our constructions can be considered as the first NISCs with the succinct CRS, but without any random oracle. Of course, we should say that our proofs are linear, I mean, rather than succinct. But yeah, we wanted to extend this idea even more to build NISQs that can achieve stranger notions like as updatable simulation soundness and updatable simulation extractability. So we started with the OR compiler that, of course, you know, these OR compilers that are quite known and traditional to build NISQ arguments from ZAPs, but they are under a trusted setup phase. So one of them is this Dealer and Slomaning compiler, which allows you to build simulation sound and simulation extractable if you use encryption scheme to encrypt NISQ arguments by using non-interactive ZAPs and key homomorphic signatures, and also strongly one-time signature schemes. So they define this language, and the prover is asked to give a proof of knowledge of witness or this CSK. That CSK is the secret key of a key homomorphic signature scheme, and its public key is given in the CRS. And as I mentioned, the prover basically proves that she either knows the witness or she knows the secret key of the public key given in the CRS, which she has used to adopt signature. This is the reason that we need to have key homomorphism, because adoption is one of the properties of these key homomorphic signatures, produced with the strange one-time signature, basically during the proof generation, to the ones valid under the CPK, which are given in the CRS. So basically, if this CSK, which is supposed to be hard in the CRS generation, is hidden, then the prover, honest prover, should use this witness. But given this CSK, we can simulate the proofs because this is an OR relation. And I should maybe mention that this mu is a one-way efficient map from secret key space to the public key space. We basically show that this result, this construction can be extended, and we are given an interactive ZAP, again, similar to the original, compiler. But now instead of key homomorphic, we need key updatable signature scheme. And then again, strange one-time signatures. The same compiler would allow us to build NISQ arguments that could achieve subversions range and updatable simulation soundness or updatable simulation extractability. Here, once we use non-interactive ZAP of knowledge, we can achieve updatable simulation extractability. And I should mention that for achieving knowledge soundness or knowledge simulation extractability, we rely on non-black box extractions that use some knowledge assumption. Maybe I should recall that this updatable key updatable signatures are just signatures that their keys are updatable, and they are defined in this fork. And you can look at, let's say, assume that actually this is shown in this fork that Schnorr with instantiated in the bilinear groups. Basically, its public key once it's G1 power X and G2 power X, which G1 and G2 are the generators of two groups. And there is a related work to this result that basically uses ZK snarks and presents updatable simulation extractable and subversions range ZK snarks. But their compiler uses the fact that the underlying proof system should achieve subversions range, which basically is stronger than witness and distinguishability that we achieve. But the positive point about their work is that their resulting protocols are succinct in the proof, but linear in the CRS, but ours are succinct in the CRS, but linear in the proof. So if you look at the description of these algorithms, our result in this section can be considered as an extension of this construction proposed in this ARS-20 paper. But we need, as I mentioned, we need a weaker security notion from the in the input NISQ, not NISQ, basically non-interactive ZAP argument. But if you look at it's the CRS generation of our resulting NISQ, it's almost the same as the key generation of the key updatable signature scheme. And if you look at the CRS update, it's again the same algorithm that the underlying key updatable signature scheme has. Basically, we just re-randomize these two keys. So you see that why we have very short CRS and very efficient key update. And in the verification, again, we have the same CPK verified. That CPK basically means this the verification of this key updatable signature that's are defined in that key updatable signature schemes. So this is the reason that we have very efficient key update, key verify, and key generation that can be done in a very huge, large-scale applications. So this results in the first updatable simulation extractable and subversion range NISCs in the succinct CRS. Maybe I should mention that we used non-interactive zaps of Grot-Ostrovsky and Sahai to instantiate our non-interactive zaps, and also Futzbauer and Oro's non-interactive zap of knowledge to instantiate our non-interactive zap of knowledge. And for key updatable signature, we use the signatures presented in this ARS. So for further details, I would suggest to check the paper. So to conclude and to introduce some future directions, we showed that the technique proposed by Belare and Futzbauer and Scafuro to build subversions range NISC arguments using non-interactive zaps can be also extended to build subversions range and updatable sound NISCs. And this basically reduces the trust in the resulting NISC argument even more. That was the main goal of their study. And the cool thing is that now the resulting NISCs also are universal, as before. But I mean, it was not discussed in that work. So the compiler proposed by Driller and Slomanin can be extended again to the updatable CRS model and build updatable simulations on an updatable simulation extractable NISC. And as I mentioned before, in comparison with the related work that was presented in ARS-20, we require witness indistinguishability in the input proof system rather than subversions range, which is weaker than that one. But I have mentioned that, again, their proofs are succinct and our CRS is succinct. So our results gets to the first NISC that can achieve subversions range and updatable simulations soundness or soundness. And this is the first NISC arguments in the updatable CRS model that doesn't use a random oracle, but has a succinct CRS. I mentioned that by now the only the construction that doesn't use CRS had CRS of size n square, which n is the circuit size. And for future research directions, so of course, one naive research question is that can we have more efficient non-interactive zaps or non-interactive zap of knowledge, because that would allow us to have more efficient instantiations and more efficient universal NISCs with succinct CRS. And the other research interesting that I think it's more interesting is can we build non-interactive zaps and key updatable signatures based on post-quantum assumptions? I mean, we had some zaps based on lattices, but not non-interactive zaps. So that would be interesting to see if we can build them, because that would allow to instantiate our constructions with the post-quantum based assumptions and results in an updatable NISC in the post-quantum setting, let's say. And for that also, we would need to build key updatable signatures based on post-quantum assumptions, that at least we are working on that direction to see that if we can build. Thank you very much for your attention. For any question, feel free to contact us.
Very good. I think you have the emails, okay, if you have any question, but if any of the audience, they have any question here, we can maybe entertain you with the answers. Okay, you have.
So in the future research, you mentioned you want to investigate how to extend your construction using post-quantum primitives, and you mentioned lattices. I saw you at a certain point you also need bilinear maps. So is this possible with lattices, and is there also any other mathematical construct beside lattices that you could use?
Of course, yeah, that's one possible direction, but we haven't built yet. We have lattice-based zaps, 2 rounds. Still, it's possible to use these 2 rounds protocols to build subversions range, but it's not as easy as this case. For that case, you need to prove the well-formedness of the first message. So one approach is to try to build non-interactive version based on lattices or isogenies or any other things. But another direction is to modify these compilers to work with 2 rounds protocols rather than 1 round. So we are trying to go with the 1 round case, but we haven't managed yet. But at least for key updatable signatures, we are more optimistic that we can build them. But haven't built this non-interactive app. This is one reason that we introduced this open question.
Thanks. Okay.